Swayam Prabha. Digital India. Educated India.
Welcome back. So, today we will start with three-phase transformer connections. So, today we will start with three-phase transformer connections. What we want to study in the transformer connections is basically, so far we have done single phase transformers, right? And in single phase transformers, you essentially had a transformer connection like this, is it not? Primary winding and a secondary winding. Just trying to get the physical diagram, just bring out the physical diagram to you, so as to jog our memory, so to say. This is a primary winding. They could be as well be on the same limbs. There is nothing like they should be on a different limb, but just because in this picture I have a primary, where is the dot? I leave it to you to think through. So, basically, basically if you think of a single phase transformer like this, and it is connected, say this is, let us say, connected to VA, and let me say this is the primary winding, I am high voltage capital VA, and this is a the LV winding VB, and now let me say that I have three such transformers, 1, 2 and 3. So, let me now this I am going to, let us say, connect with B phase, and this I am going to connect with C phase. Now, this will be VB, this will be VC. Now, the question is that the three phase windings are again interconnected, right? You have studied the delta connection and the star connection. So, it is possible that the primary side and the secondary side, this is connected in a star configuration, this is connected in a star configuration, this is connected in star configuration, this is connected in delta connection. Usually it will be grounded through, so, or this side also I am grounding it, or you have this in delta, this in star, or you could have a delta delta connection. So, what I mean to say is you have Y, it is called as YG, just to emphasize that there can be a connection which is without the grounding also. So, YG, this will be called as YGD, this will be called as D y g, and this will be called as d d. So, you can have connections like this. Now, let me take one simple interconnection which is based upon the let me take a simple interconnection which is based upon y grounded. So, I am going to let us say I do this y ground, and I also ground the other side. So, I have connected a y ground interconnection. Now, this is my A phase, this is my B phase, this is my C phase. So, if you are asked what is the vector diagram as it is called for this interconnection. So, let us say that I show this as V A, this is balanced 3 phase supply, V B lags 120 degree, V C equal in magnitude as V A and V B leads 120 degree, and let us say the turns ratio is n is to 1, n is to 1, and let us say it is a step down transformer. So, then sorry. So, what I am saying is now this will be your, because it is I have taken it as a step down transformer. So, this will be your V A, V B and V C, and the turns ratio is n is to 1. So, V A will be equal to V A by n, V B by will be equal to V B by n, and V C will be V C by n, and the inverse relationship will be applicable. This I A will be n I A, I B will be n I B, and I C will be n I C. Usually in this coming lecture, as you will see as I go further, I will use capital N as a notation for 3 phase transformation ratio, and you will see this in more detail. It can even be a complex quantity, but in this particular simple example, n is equal to n. So, it does not basically there is only one transformation ratio. Until I start doing one side delta, another side star and so on, a root 3 factor is not going to come into picture, but once I sort of connect the primary into star and say secondary into delta, then you would see that there is either a multiplication factor by root 3 or a division factor by root 3 which comes with respect to n. And another very important concept which I want to show is in this lecture is that when you have such a delta star connections, then you will get usually a 30 degree phase shift also. So, in that sense you can even say that the turns ratio has become complex. Though we will usually like to say that turns ratio is root 3 and there is a separately we will make a statement that there is a phase shift of plus minus 30 degrees. In fact, it depends upon how you interconnect your delta winding. You can create different levels of phase shift. There is something called zigzag connections also, and there are a lot of three phase transformer connections. There is very interesting topic by itself. I am just giving you a preview, whole of it I will not be doing in this course. Now, and therefore, primary, for example, if you look at it as a 12 o'clock, then so if you divide 360 by 12, then it is a 30-degree connection. So, you could have secondary like 30 degrees this side, secondary could be 30 degrees this side. So, you will say it is 11 o'clock or 1 o'clock and so on and so forth. So, it is also these connection phase shifts are sometimes described by clock diagram also. But I am just going to take one very simple 30-degree phase shift, and I am going to consider only that interconnection which in which the IEEE or the ANSI standards say, because the different interconnections and phase shifts are created for different application purposes, complex application purposes like in power electronics or specific places, but we will stick to the most 99.99 percentile of the time used things, because we are doing a first course. So, the IEEE ANSI standard for such connections basically say that the HV side in a star delta transformer, the HV side should lead LV side by 30 degrees. This is what they say. The idea is a very simple idea is there. I will explain it to you. Let me create a very simple transmission system with two generators. This is called a single line diagram of a 2-bus power system. Basically what it means is of a 2-bus 3-phase power system. What it means is, I call this as bus 1, bus 2. A bus is basically the word comes from the term bus bar. It is a thick copper cable, copper interconnector on which multiple devices can come and get connected. So, this, to show that it is thick, maybe I will thicken it a bit. So, these are the two buses, and what is interconnected to it? What is interconnected is, this is a transformer, this is called a transmission line, this is a 3-phase transformer, this is a 3-phase transmission line, this is a 3-phase generator, this is also a 3-phase generator, and there could be any load, your residential application, a big industry, a big city, whatever, these are the loads which are connected to it. And power can flow on this transmission line, 3-phase transmission line, this or like this. So, because it is a 3-phase transmission line, and you must have seen 3-phase towers and so on and so forth. So, there will be 3 conductors A, B and C, or they could be in a horizontal A, B, C, supported on a tower. You must have seen towers and transmission line structures, but in the diagram it is just shown as one line. Similarly, this is a 3-phase generator, means it has 3 voltage phases VA, VB, VC, all of equal magnitude lagging by 30 degrees, that is the way they generate balanced voltages connected here. This is a 3-phase transformer. So, the 3-phase transformer is a transformer. 3-phase transformer is something, either 3 independent transformers connected in one of the many combinations like this, and then there is a, like for example, star zigzag, y z, this could be like this is zigzag connection. This I am not going, at least right now I do not have any idea of diving too deep into it, because we may not have time for it. And so this is a 3-phase transformer like this. For example, for what I have written, I would write it as YG here, and I should have, I am sorry, I should have had a transformer sitting here also. What is this? And again, this could be like, for example, a delta winding, or it could be a star winding. Let me say that this is also a star grounded. So, the 3 generator windings are connected in star, and these are also connected in star, and let us say this is a YG connection. So, now suppose there is no load. Suppose no load, generator voltages are equal, generator voltages means at the terminals, if you just open circuit it and check what voltages they are going to generate, they are exactly the same voltages that they are generating. For example, if it is a 3.3 kV 3 phase, means Y connected, line voltage is 3.3 kV, both of them are generating 3.3 kV, and let us say that this is being stepped to 220 kV, again line to line 3 phase. Then if there is no load connected on it, this will be also some 220 kV, and this transmission line obviously has some length. So, it could be like, for example, a 100 kilometer line or something like that. This is the 3-phase transmission line. Now, for the time being, since I have not connected any load, the mechanical input to the generator is also 0, because the electrical output from the generator is 0, and I am ignoring the losses in the transformer and line. So, therefore, no power is flowing to through the line, or it is being drawn by the load. So, it is called unloaded system as it is. Actually, power will be flowing towards it, usually in a loaded system. But now, if you look at it, if you look at the voltages which are available here and the voltages which are available here, the 3 phase voltages which are available here and here in this unloaded system, what you would see is they are exactly identical, because I have made it symmetric around it and it is unloaded. So, the 2 voltages are exactly identical around this line. So, no power will flow across the transmission line, no current should flow across this transmission line. And this symmetry is what has ascertained that in the unloaded system no current is flowing in the transmission line. But now imagine that I did YGD connection here. That means, this one side of this winding, I went for a delta connection. So, let us say I connected it like this. suppose I connected it like this. So, then what would happen now? There is a asymmetry in the connections on the primary side and the delta side, and I am going to show you that 30-degree phase shift how it comes very soon, but that 30-degree phase shift will come into play, and so the voltage will turn out, though the magnitude of the voltages are going to assume that the turns ratio have been adjusted. Now, there could be asymmetry in the magnitude of the voltages here, and if there is a difference in the magnitude of voltages and a line is there and there is a path for current to flow, it flows like this, goes to the ground, flows back through the ground and comes back. So, if there is a path for flow of the current, then obviously, if the magnitudes are different, current will flow, losses will happen, and you can see that even when the system is unloaded, there is no load connected, the generators will need mechanical input power to sustain the losses, and this is a asymmetric operation which is undesirable, because in a balanced condition with nothing loaded on it, and you would like to see everything symmetric, currents being set to 0 and so on and so forth. Just think of it like, suppose there is some asymmetry and your meter is there in your house and you are not connecting any load to you have not switched on any load in your house, but yet your meter starts showing up some bill because there is asymmetry. So, there is some current flowing and therefore, there are some losses happening, and those losses you have to pay for. So, that this is not acceptable, this is not acceptable. Therefore, if you connect it, if you connect a transformer here like this, the another option is you should connect the transformer exactly in the same way in the other side also. So, this is my LV side, this is my HV side, this is my LV side, this is my HV side, and I want to connect transformer exactly in the same ways in the both the sides, so that both the magnitudes of these voltages here in the unloaded conditions are same, and the phase shift should also be same. If suppose one voltage is like this, phase angle should also be same, and suppose the other angle is like say same magnitude, but 30 degrees away from it, then you can again see that there is a difference in the voltage, which is this, and once there is a difference in the voltage, which is this, due to the phase difference between the two, then what is going to happen? Current will flow, will create losses, will have to be supplied. It is an economic loss and difficult to analyze such a circuit even under loaded conditions, and what you cannot analyze properly, you will not know whether it gives you some surprises in the field while in operation, some surprises, unpleasant surprises is what I mean actually there, and therefore, you will not want it. So, the IEEE or ANSI has clearly stated that, and I did state that I think somewhere already, HV side should lead the LV side by 30 degree. So, let us say nominal voltage either on the LV or HV side is called 1 per unit. That means, nominal is treated as 1. So, if the voltage is 120% of the nominal value, we will say it as 1.2 per unit. If it is 95% of the nominal value, we will say it as 0.95 per unit, and so on. So, the discussion does not directly now involve talking, array this is 3.3 kV, this is 400 kV, this is 220 kV. We do not have to directly get into all that kind of a discussion. So, coming back to advantage of this is, you will see if you, as you progress in power systems course and so on and so forth, you will see that per unit system is something very common in power system analysis to discuss, because that way different equipments have different ratings, but by properly fixing their base nominal base values properly, we can do all of our calculations in per unit, and then the numbers are voltages are close to 1 per unit, which is much more easier to handle and analyze. Okay. So, coming back to this, if however let us say while going from primary to secondary, 30-degree phase shift happens here on. So, LV to HV, what we have said, HV should lead. So, if this is HV, suppose this is your LV side, the generator, and the HV should lead in per unit, both the voltages are 1 per unit only, but it leads now by 30 degrees. Now, if once I fix that this is the way I want interconnection of transformers to be done, you have your delta stars and you have a complication that you can have circulating currents which are flowing. This currents which I just discussed are called circulating currents. I mean, they are not delivering any power to the load, they are not directly going from source to sink, but they are just in a way even in an unloaded system circulating, and this creates a problem. And so you fix this convention that the HV should lead LV by 30 degrees. Now, because you fix this convention, this is your primary side, in per unit this is exactly what your secondary side will be. And now you can see that there is a transmission line connecting this HV to this HV. This is the generator, this is your generator. So, here is your generator, here is your generator, it went through a transformer, this became the HV voltage, this became the HV voltage. Since their magnitudes are equal and the angles are also equal, so when I have this transmission line interconnecting this, I have a transmission line interconnecting this, under unloaded condition there will not be any power flowing through this transmission line. So, therefore, it is very clear that this circuit will behave truly like a unloaded system or a supply when there are no loads connected to it. So, to achieve this symmetry and to achieve error free, see the power system has hundreds and thousands of transformers and transmission lines. Unless you fix something, unless you standardize or fix something like this, people will err, not deliberately, but will happen, people will err, and then you will have circulating currents, and they can create significant amount of trouble not only in analysis, but they will create a problem not only in analysis, but also the operation of power system. Power flows may cross, line currents may cross the rated value, protection systems which are installed to protect these transmission lines, transformers, generators during faults. These faults will happen on these systems because they are exposed systems. Your most of the transmission lines are overhead, or most of the distribution lines that you see in your houses coming are overhead. Only very few places you have underground systems, like Mumbai distribution for example is an underground system, and that is very good because it gives you much higher level of reliability, because winds, rains will not directly cause a damage to the underground system, but most of the power system is overhead and exposed. So, winds, cyclones, faults, even heat, temperature, sagging of conductor, tree touching a conductor, snakes or birds creating short circuit between multiple phases, all such things will create faults which are large currents which can damage the equipment because of the heat and the forces that are generated in it. To prevent a system from damage, there will be a protection system which will open these lines or these devices using some switches which are known as the circuit breakers, and the protection systems have to be very delicately and properly set, and for all that this circulating current will create a mess or a problem. So that is why in a nutshell I think I have told you very clearly that HV side should lead LV side by 30 degrees. This is very important. This is convention is now fixed. So, we have to just keep, if we keep interconnecting the transformer such that this happens, we make sure that under unloaded condition no circulating current flows in the power system, and this concept will be expanded in a power systems course. So, right now I will not expand this concept by taking multiple number of buses and a 4 bus system or a 6 bus system and show it to you. So, we will leave this topic here and come back to the transformers. Now, these 3 phase transformers could also be auto transformers. I mean, I have discussed to you advantages of having auto transformers. They are compact in size, they increase the rating, efficiency increases and so on and so forth. So, they could be as well be auto transformers. That does not really make a difference to the discussion that I am making here. The construction point of view, they could be 3 independent transformers, they could be auto transformers, or you could have a 3 phase transformer which looks like follows. There are 2 possible constructions for 3 phase transformers which are commonly used. You can directly buy a 3 phase transformer, it will be cheaper than buying 3 single phase transformer, not because of the economics of the negotiation that you do with the buyer that I am buying 3 pieces and not 1 piece, but because the construction and the geometry can be optimized and actually the cost can be cut down. So, 3 phase transformers are of typically 2 ways, core and shell type construction. So, in the core type construction, you just have this is the, let us say, the first limb, one, 2, 3, 4, 5, 1, 2, 3, 4, 5. One, 2, 3, 4, 5. So, I have so let us say this is the A phase primary, this is the A phase secondary, this is the B phase primary and this is the B phase secondary, and I have a third C phase winding which is also like installed like this. So, you can say this is VA, this is VA, VB, VB, VC, VC. Now, this is all my iron core, right. These are the 3 limbs or cores or 3 limbs core type in the 3 cores. So, this is where the magnetic path is going to go. So, if you look at the strictly speaking, the A phase and the A phase flux will come like this for the time being, B phase flux will come like this, the C phase flux will come like this. Okay. Now, let us for the time being assume that I have not connected anything to the B phase or the C phase. Then what will happen? This flux will go like this, will break into two parts, and if the iron is considered to be ideal, then by symmetry it should break into two half and half, assuming any little minor variations will cause that to happen, otherwise it could break in any arbitrary way. But because no devices are ideal, we can assume that it will break into two, but the any non-idealities are also symmetric. So, therefore, we can assume that if this is phi A, then this will break into phi A by 2 here and phi B by phi A by 2 here. So, what I am trying to sort of say is that this phi A has traversed broken into phi A by 2 here, traversed, traversed only back, so the phi A traversed became phi A by 2 here, phi A by 2 here, returned again came back as phi A. I am sorry. Returned and came back here as phi A. This is phi A by 2. You know all that. This is phi A. Now, look at the, suppose you just excite the B phase with B phase flux values. Taking this as a equivalent of y, the y r y b. So, you take this as the y values, you excite it by the so the phi b is here r y b or a b c, then it will break into phi by 2 here, it will split into phi by 2 here, will return back from here, it will become phi by 2, in this limb it will become phi by 2, and it will come back as the phi by 2, it will come back as the phi by 2, which is which will turn back here. And finally, let us look at the third limb. So, the phi b will come here, will move phi b here, will move as phi b here, will split phi b by 2, phi b by 2 will move here, phi b by 2 will move here, phi b by 2 will move here, and these are the three R y b. Individually, if each one of them were excited, then this is how the flux profile will be seen. Now, this is a symmetric device, this is balanced device. So, we assume that RMS values or the peak values of all the fluxes in the three phases are same, but they are phase displaced by 120 degrees, and they all are basically phasors that we are representing, which means that they are actually, these flux waves are also sinusoids. So, now if you look at the, let us say, so if you are talking of phi a as the reference phasor, if you talk of phi a as the reference phasor, then phi b is a square times of phi a, where a, you recall, is 120 degrees rotation operator anti-clockwise. So, a square is 120 degree lead, sorry, a square is 240 degree lead or 120 degree lag. So, phi b, therefore, because the phi b phasor has to lag the phi a phasor by 120 degree. So, therefore, I am writing it as a square phi a, and phi c can be written as a times of phi a. So, now let us look at the first, the limb. There are three limbs here, right, limb 1, limb 2 and limb 3. The limb 1 has A phase windings on it, limb B has B phase windings on it, limb C has C phase windings on it. So, if I look at net flux in A phase limb 1, it is phi a minus phi b by 2 minus, this should have been, the third one should have been C, I am sorry. A, B, C, so this is phi C, this will become phi C by 2, this will also become phi C by 2 and phi C by 2, phi C by 2 returns here, and I am sorry, this is going to be phi C is being returned here. So, phi A minus phi C by 2. So, therefore, the flux first limb created phi A, the second limb created a return of phi B by 2, and the third one got a negative direction return of phi C by 2. So, therefore, this flux is going to be equal to phi A minus phi B plus phi C by 2, phi A minus phi B plus phi C by 2, which is equal to phi B can be written as because they are balanced, and you know that 1 plus a square is 0, 1 plus a square is 0, 1 a square a, vector addition of this is a equilateral triangle coming back to the same original point. So, therefore, the phasor sum of this is 0. So, therefore, you can write phi a plus phi b phi c as minus of phi a minus of phi a. So, therefore, this will become 3 by 2 times of 3 by 2 times of phi a, correct? Am I right? I think I am right. Phi b by 2 comes here, phi c comes here, phi c by 2 also comes here. So, they are additive, phi is there. Okay. Now, let us look at, so similar picture you can develop for yeah. So, what it basically means is, look at this very carefully. Now, I said this sum of these 3 is 0. So, this becomes the net is equal to this is equal to this. Now, let us look at what happens in the horizontal limb, in the horizontal segment. Let us see. Similar picture you can write for after superposition for the vertical B limb and the vertical C limb. Now, let us see what happens for the horizontal segment. In the horizontal segment, this is phi a, which is flowing, phi b by 2, which is flowing, which is reversing back, and phi c by 2, which is also phi c by 2, which is also reversing back. So, therefore, the phi a minus phi b by 2 minus phi c by 2, which is again the 3 by 2 phi a would come out here, 3 by 2 phi b will come out here, and on this one 3 by 2 phi c will come out here in this direction, right. So, if you look at, say, at the center junction connection, you will get 3 by 2 phi a, 3 by 2 phi c, and 3 by 2 phi b coming here. But what is phi a plus phi b plus phi c? It is equal to 0. So, therefore, your law of conservation of flow, the equivalent of flow of conservation of flux, equivalent of your KCL, is satisfied. So, therefore, this device will not give you any, except for designing the flux levels the way I just mentioned to you, to take care of the superposition effects that I just mentioned. So, you do not want the core to go into saturation. So, if the net fluxes are somewhat higher, then the area of cross section has to be taken care of in that particular way. But other than that, you can actually the device will not have leakages which are happening. The point which I am trying to say is, see, if these fluxes would not have sum to 0, then where do they go? Then they have to flow out through the air outside, through the tank outside and then close the paths and come back, right, because the fluxes are just in our magnetic circuits, we are just treating them as using Kirchhoff's current law only. And if the fluxes dissipate into tanks which are outside, then they will they are not laminated cores, so they will create significant amount of eddy current losses and so on and so forth, heating, and that will be hot spots, and you will have trouble. Plus leakage will create degrade the efficiency of the transformer, will not cause it to work properly. The regulation will become poor, the leakage inductances will become larger. So, you will have other kinds of subsidiary problems which will come into the picture. But by taking note of the fact that phi a plus phi b plus phi c is 0, at I can show that at each of the nodes, I showed it for the center node, but it is equally true for all the, it is the law of conservation of flow makes clear to us that this these there is no, the superposition is not going to cause any leakage of the flux outside in the outside environment, the tanks and the air and so on and so forth. So, I can actually, I do not need 3 single phase transformers like this. If I had 3 single phase transformers like this, then I need 6, 1, 2, 3, 4, 5, 6, 6 central cores are needed. But now I have optimized my construction by only having 3 central limbs and 4 horizontal limbs, while here I had 6 horizontal limbs. So, the magnetic is not actually has not become, you can see that there is a saving in the material which has happened. Now, another construction, 3 phase construction, is known as shell type construction. In the shell type construction, I should make it a bit smaller. Okay. And I need a enclosing so I have a R limb, Y limb and B limb here. Now, the difference here is that this flux will break and have a return path like this. So similarly, this flux will come here and then it will come like this, but will not fully burden this, it gets another path to come like this. Similarly, this flux will break, will get two paths to come, it will not come directly start flowing leftward, because there is a other link to break it through. So it will break here, then it will break here, it will break here, and then it will come back, and then it will come like this. So the shell type has uh, 5 vertical limbs to reduce flux densities, or rather fluxes, flux in vertical limbs and horizontal limbs. So there is additional path provided on the side, and so any unbalances, see, because real life operation will have unbalances, right. I mean, if you look at even your body, your left hand is not same as your right hand, your right nostril is not same as your left nostril, your right leg is not same as your left leg. There is always some unsymmetry in your posture. You may be putting a bit more load on your left leg than the right leg, or vice versa, or you are predominantly a right hander or a left hander. So you see that though it on the face of it we look symmetric and so on and so forth, there will be unsymmetries, unbalances even in the usage. Though it looks symmetric, the body looks symmetric, in its usage there is unbalances. I tend to favor one side a bit more, I sit a bit this side, or I look a bit more this side, and so on. So same thing is going to happen in our device operation, even though constructionally we make them symmetric, we think of putting symmetric supplies, but there will be some variations, some unbalances. Any unbalances will come into operation. The core type transformer is somewhat challenged here. It requires this, for things not to leak outside, it requires a very good symmetry, but here even if there is some unsymmetry, the leakage can happen through these side limbs, and therefore it will not go into transformer tank or create some other anomalies which you have not properly analyzed. The flux path will still be in the designated, the flux paths will be still in the designated iron limbs that you have created for them. So both three phase and shell type transformers are in use in an actual system, and sometimes actually, though I have not discussed constructionally this part very clearly, but let me just make a mention to you that constructionally many times this LV winding will be in the inside, then there will be insulation layer, there will be some insulation layer, and then there will be the HV winding which will be superposed over it. So what I mean to say is, your core, iron core is at ground potential. So the core is at ground potential, then comes insulation, then LV winding, again insulation, then HV winding. So, this way the gradient is of the voltage is proper. So, the insulation gets properly designed, and it is not necessary that the LV winding should come first and then the HV winding should come below. It can be like this is the core, first I have a LV winding, then some insulation, then I have a HV winding also around it. There is a lot of things, innovations that can happen in the construction, and we can only peep here and there a bit into it, and we will stop here for now. Our time has run out, we will stop here for now. The 30-degree phase shift we will explore in more detail in the next class. Thank you.